Welcome back to the classroom. My name is Mr. Wong. Today we'll be going through the Module 7 Inquiry Question 3, which looks into, if you can actually look at Wend's law, it looks like the quantum nature of light, basically. Okay, so the very first question, it says, describe the difference between the spectra of light produced by a gas discharge tube and an incandescent light. So with a gas discharge tube, if you want to think about it, a discharge tube presents specific wavelengths. Okay, I might actually write it here. So with the gas discharge tube, and I'll do it sort of like a table format. Okay, with the gas discharge tube, we get specific wavelengths of light. So specific The way we get this specific wavelengths of light is produced by the electron transitions within the light source itself. In the case of an incandescent light, if you've ever seen one, it's basically these big light bulbs, the really old light bulbs that actually use the heating filament to produce the actual color of light. So this one, the light is produced by heating up a metal filament. And what we actually know is if we produce electromagnetic waves that produce or give us the sense of heat, that means the wavelengths produced are more favoring towards the red wavelengths of light and even infrared light. And I guess what we can also say is it's a greater intensity in the red light spectrum. Doesn't mean there's not other colors, while as the transitions that we get here, majority will be of similar color or similar intensity. Obviously some might differ. So that's the main difference between a gas discharge tube and an incandescent light bulb. Let's move on. The graph shows the curves predicted by two different models, X and Y, for the electromagnetic radiation emitted by an object at temperature 5000 Kelvin. It says identify an assumption of each model which determines the shape of its curve. Okay, so model X is of old classical physics. Old classical physics basically predicts that energy is related to intensity. And so if I get more and more energetic particles, if I'm heating something up more and more energetically, it's going to vibrate more and it's going to emit a greater intensity of light or more energetic light. Model Y here is the composition of a black body radiation. And what we see here is the first idea that energy is actually quantized. So the reason why we have a peak here is because this is the point at which the transitions or the oscillations in the atoms, at least that's what they thought at the time, were at its maximum. The reason why there's a drop off down here is because these transitions, these really high energy transitions, were less favored. Okay, and you can sort of see with the lower energy ones, if we draw a line through where it hits the peak wavelength or the peak intensity, we can see there's a much greater quantity of the lower energy wavelengths of light being produced. And the reason being is the electron transitions are a lot smaller, and so this on this side is a lot more favored because it has less energy. Okay, so identify the assumption of each model which determines the shape. Let's write them down. Okay, so let's go through model X. Now what this is representing, if we can say that energy is related to intensity, we're saying that when energy is absorbed or emitted, the energy is continuous, so it will continuously grow to an infinite amount. Whilst this one here, we represent that energy absorbed or emitted is quantized. It's capped at a particular level. Okay, so let's go there. So model X represents electromagnetic waves, radiation, emits and absorbs energy in a continuous manner, and they believe that energy was related to the overall intensity, while as model Y viewed that electromagnetic radiation that was emitted or absorbed came in quantized amounts. So electromagnetic radiation emitted or absorbed is quantized, and they believe that energy was proportional, and we'll just do that. Energy is proportional to intensity. Energy is proportional to frequency of that electromagnetic source. Okay, so that's how you do that question there, and that's based on our understanding of these two models here. Okay, question C. The diagram shows the radiation curve for a black body radiator. Black body radiator means something that will give off all ranges of electromagnetic radiation after absorbing all forms of different color variations, and at a temperature of 5000 Kelvin. It says on the same diagram, sketch a blackbody curve for a blackbody radiator at temperature 4000 Kelvin and explain the differences between the curve. Now before we get into drawing that, what we must first do is work out what the peak frequency is. The peak frequency is given as the constant, Wend's constant B, divided by T, which is the absolute temperature, 4000 Kelvin. So 4000 Kelvin divided by Wend's constant. So Wend's constant is 2.898 10 to the power 3. Okay, so plug it into our calculator. I'll write it down here actually. So we get 724.5 10 to the power minus 9 meters. That's the same thing as saying we have 724.5 nanometers. So if we find that on our chart, it'd be around a range around here. The next thing we need to work out is what could the potential intensity of the graph be. Okay, so we'll have a graph along the lines of around this region here. Okay, it's going to drop off, and this is going to once again elongate going along there. Okay, so there's that. That's our peak there. Now obviously we need to look at what the differences is between the peaks. Well, we can see from the peaks that the 4000K one, it has a higher wavelength or a larger wavelength for its peak wavelength. So 4000K higher maximum wavelength. And the reason why we know that, if you can actually see, as temperature decreases, the maximum wavelength increases, because the maximum wavelength is inversely proportional to T. So if max goes up, that's because that's due to a drop in our T value in comparison to the 5000K. Okay, I guess the last bit we can show for is why is this lower than the 5000K region. Obviously we want to explain the difference. The reason why that's the case will demonstrate that there are less or lower transitions occurring at a lower temperature. Okay, so the overall, I guess the overall peaks at each point. So overall peaks, overall area, let's say the area underneath the graph, overall area under the graph, okay, so that's our response there. Using our calculations of Wend's law, we can actually work out the peak wavelength. From there, we can explain why the wavelength here is bigger than the 5000 Kelvin wavelength. If you actually have a look at it here, it's 5000. You can actually calculate it out. I'll write down the number there so we can do that comparison. So the lower the temperature, the higher the peak wavelength is. That's why ours is shifted more towards the right. Also, the reason why our curve is lower is because the intensity of the light would be less, and so we would have less transitions as well. Okay. Okay, so in comparison, our 4000K had a wavelength of 724.5 nanometers, which was bigger than our 5000K, which had a wavelength of about 580 or 500 and oops, let's change that, 579.6 nanometers. Okay, and that's because our peak wavelength is inversely proportional to temperature. So that was our graph, and that was our written response here. If you found this video useful in demonstrating how to go through HSC exam questions like this, please give this video a like, and I'll see you next time.